go like towards me.
Yes, yes. Wait, into the page. As my view, I'm seeing
Oh,
the screen into
okay.
the screen. So you can use the left hand rule yourself. Check if the force that you determine is also in the downward direction.
I get
Into the page, into the screen. Feel the force is downward.
oh yeah, downwards. Yeah. Mm.
Okay, so this is
Yeah.
just a testing of how we use the left hand rule,
Mm.
explaining the magnetic force. We can explain this force by thinking about the magnetic fields of the magnet and the current carrying conductor. Okay, when the charge move, forming an electric current, the movement of those charges will generate a magnetic field, as we already know in the beginning of this chapter. Okay, a current, a flow of charge, can generate a magnetic field, and this magnetic field interact with the magnetic field of the magnet, an external magnetic field, like the interaction between two magnets. Okay, and
Yeah.
therefore the charge, which is the reason, the cause of the magnetic field, will also be acted on, exerted on by the magnetic field of the external magnet, and the charge, the current, can be drawn in a certain direction. Later, we will see that the magnetic field also acts on individual moving charge particle, not just a current, because the current is basically a flow of a lot of charge particles, trillion particles. Okay, so each individual particle is also acted on by a magnetic force when that particle move in a magnetic field. Okay,
Yeah.
magnetic. These fields combine or interact to produce the force on the rod. Okay, the external magnetic field, the magnetic field, the current conductor, and combined fields. Magnetic flux density. The letter B here uh, is called the magnetic field strength. It is a magnetic force acting on a 1 ampere unit current running in a 1 meter length rod. Okay, but it also has another name called magnetic flux density. Yeah, magnetic flux density. The magnetic flux density is rector close to the pole of a bar magnet and gets smaller as you move away from it. Okay. So here was what I was talking about. Okay, dividing the force and the current and the length. So the flux density is a force acting on 1 ampere running in 1 meter length. Okay. So this is the definition. Experience per unit length by strong straight current conductor carrying the unit current, which means 1 amperes, and placed at right angle. Because in the equation of magnetic force, it involves the angle, the sine of that angle. So we want to define B, the magnetic flux density. We need to place that rod at right angle with the field. Okay, that's the definition. So this is about understanding what it means. This is one of the most important concepts in this chapter, magnetic field. Okay, and there will be some like multiple choice question asking about which statement is right, the correct definition of magnetic flux, for example. Okay,
Yeah.
and also it will remind us about this equation. And I'm kind of sure that this equation is given in the booklet formula.
Oh,
Measuring B with hole prop. Okay. I think we should do this thing first. And this question, haven't we done it? No, not yet, right? Okay, we'll do this thing first before moving on to the whole effect here, to a method to measure the field B. which we can also make a whole prop ourselves, DIY, do it yourself, pretty simple. Okay, but let's answer the question first. You should install Skype, or do you KakaoTalk, right? I have an KakaoTalk installed in my computer, so you can send take a photo and send your solution to me via KakaoTalk, or yeah, you can install Skype and send the photo directly.
Okay.
Let's see. Drop. This is my number if you want to add me on KakaoTalk.
Well, I actually don't have KakaoTalk, but I have Zalo.
Okay, that's good. Even better,
Yeah.
because it's like the sanctuary of Vietnamese people. Yeah. Also, the number I use for Zalo.
Yeah. Do I just add you on?
Yeah, definitely.
Okay.
Take the phone. Flux density coming there for a while.
Okay. Oh, it says that the number is not linked to Zalo.
Let me check it. Probably I sent the wrong number. Sorry, that's the wrong number.
Oh, okay.
One wrong number. Yeah, only like one missing number last time.
Oh, okay. Yeah, I sent you on some.
Okay, I got it. Let me accept the friend request also. Looking for a way to rotate. Okay, here it is. PI 0.6 Tesla, current 0.2 amperes, and the length. Okay, you forgot the unit of your force. The next one, question 6. Knowing this thing, calculate the field 10 to negative 2 divide. I think that's just the matter of using the calculator. I don't think you will make a mistake with the calculator, right? 0.8, 0.08 Tesla. Okay. 7. Right angle 10 to 18 electrons, carrying current 1.6. That is the charge electron multiplied with the number of electron, which is the total charge. What current is flowing? The question is the current. The Y line magnetic flux density in each second. Okay, each second. So you should not write like divide 1 second, because basically the number of electron per second. It is okay, but it helped the graders, the teacher understand the calculation better. And the unit of current is ampere, not coulomb. 1 ampere is 1 coulomb of charge, which is 1 trillion electron here, 10 to 18. Okay, divide 1 second. So there's a wrong unit here. And question B, what force act on the Y? Use the equation FBL, BIL. This is the 10 to negative 3, but Y negative 3, this is the length, right? The length of the Y, 50 centimeters. So you just need to times 50 with 10 to times negative 2, which is a 0.5 meter, not 10 to negative 3, right?
No,
that's the length.
Yeah.
Sorry. 1 second here. The density. Okay, we see the field. So times net 3 to convert into Tesla. We see the length of the Y and the current. Okay, the current is here. Negative 19, 18. Okay, or you can write 0.16. Okay, no problem for those problems. Okay, the next one here is measuring the flux density with hole probe. This is the hole probe. Similar divided in magnetic flux, magnetic field. Arrange between flux density in laboratory. They didn't describe. Okay, so this is just the information about the device used to measure the magnetic flux density. This is called a hole probe.
Okay.
And you connect it with a meter here, and simply just put it in the magnetic field between the two magnets here, and then the meter will the needle will deflect an angle and show the value in volt. And later, if you do the paper like paper 3, paper 4, you will see the question related to the principle, the working principle of that hole probe, but not for now. So we will look back on how it works later.
Okay.
When we do the exercises. Micro Tesla, milli Tesla to control box. Okay. This is the arrangement of the experiment to measure the magnetic flux density in a simple way without using the whole prop. We will use the equation F equal BIL. Okay, if we put a magnet on a weight scale and adjust the weight scale so that the initial value is 0, of course the magnet has an initial weight, for example 300 grams, but we intentionally change the reading of the balance to neglect the mass of the magnet. Okay, and then we put a electric wire above the magnet and then connect to a power source. Let the current run in that wire. The current will generate a magnetic field. Okay, and that magnetic field will pull the magnet up or push it down. We can intentionally change the direction of the current and therefore change the direction of the field, casting a push on the magnet. Therefore, the reading of the mass scale here will change like 100 grams. Okay, so we initially adjust the scale to be 0 so that the reading later is just the value equivalent to the force that the magnetic field of the current interact with the magnet. Okay, you got it?
Okay. Yeah.
Yeah, so this is the tool. Simply use a mass scale to measure that force, the force F. We measure the current simply with the ammeter. We know that, right? The ammeter. And connect here with a variable power source to control the current so that we can have different values in a data table. Let me illustrate that on the board here. We have a table of, we want to measure the field B, okay? We have the equation force equal BIL. When the angle in 90 degree, the current is at right angle with the field. So the field B, the flux density, is F over I and L. So we need to measure the current and the length. The length is very easy to measure with just a ruler. We can also change the length, but we only need the current. So we have data table of the current and the force, and then the other column we will calculate the field with a given measure length, for example 0.5 meter. Okay, so we value measure the current like I1, I2, I3 many times to reduce the random error. Okay, and we measure the force F1, F2, F3, etc. And therefore we can calculate the field. The force is measured by that way. Do you understand it?
Oh, yeah, I do.
Yeah, okay. I can show you a real experiment on a video YouTube also. We can find almost everything on YouTube.
Yeah.
Magnetic force measured experiment. Yeah. And yeah. This is a transformer. This is a electromagnet, not a transformer. Okay, electromagnet. So they use electromagnet to generate the magnetic field instead of a permanent magnet. This is a wire frame connected to a power source so that the current will run in this frame. Okay, the magnetic field is generated by this electromagnet down there, and there's a magnetic field, uniform field in this gap in at right angle to the part of the frame here. Okay.
Yeah.
It will provide a magnetic force in the downwards direction or upward direction. We can change that. We can adjust the direction of the magnetic field because simply by switching positive and negative terminal, reversing the direction of the current. And therefore, the magnetic force will pull the frame down, and it is hanging to a mass scale or force scale so that we can measure the force.
Oh,
adjusting the current here. The current is huge, like they start from small current and then can gradually increase the current. Okay, this is the diagram of experiment. Okay, the magnetic field down there will pull this frame where the current run in down. Okay. And we will collect the values. They even use a digital sensor to measure the force, and those values of the force will be recorded in the software. Very advanced technology, huh?
Oh, yeah.
And we will have the relationship between the force and the current, which is a beautiful linear relationship.
Mm.
And then they will type the other variables, which is the length and the let's see, what is this? Millinewton. Wait, let's complete seeing that. Per ampere, millinewton per ampere. What's that? Newton per ampere. Like force per current, which is here F over I, huh? And then divide the length as well, and you will get the field B. Because this is, sorry, I haven't shared with tab here. So F over I is the millinewton per ampere here, meaning the current running in 1 meter length, and then divide the length L also, you will get the, wait, this is the force on 1 ampere, like force over current. Okay, this is the graph of the force over, wait, millinewton. Oh, just the force. This is the current. Okay, so that's the principle. And from the gradient of this graph, we can calculate the field. Okay, yeah, share it up. So if we plot a graph of force and the current here, we have a linear relationship where the value can distribute on the two sides of this best fit line. And if you do the paper 4, you will need to draw the error bar also.
Yeah.
Okay. The gradient is delta F over delta Y, delta I the current. F over I. Oh, so wait. According to this relationship, it's not a linear relationship. Sorry. Wait. Okay. F here equal to B times I times L. Yeah. So if making Y a variable, let me write it at the end of the equation. B L I. I here is like X. X is like Y, huh? This whole thing in the gradient.
Oh, okay.
And multiply with X, Y equal gradient times X. That is the linear relationship. Gradient equal to B and L. That's it. The method to measure the magnetic field intensity with simple tools. Measuring B with the current balance. That is this way. If it's magnet on yoke, current gap, symbol of the current balance. Okay. Force magnetic field with the current balance. Basically the same thing, but just simpler and probably less accurate than the advanced experiment there. Okay, current crossing field. Okay, when the current is in the same direction, parallel with the field, the angle is 0, sine 0 is 0. The force acting on this part of the current in parallel with the field. Okay, but the other two parts of the current at right angles to the field, on left and right, experiences two forces up and down, because the direction of the magnetic force depends on the direction of the current, which is described in the left-hand rule. Okay.
Yeah.
So using this property, the direction of the force, we can invent. Actually, they did, the scientist, the engineer, invent the electric motor. And some other question down here. Electric motor, it will be the next. Let's do this question first before. Electric motor. Okay. So please do question 10 and 11 yourself, and also send the photo to me.
Okay. How long have you been teaching like physics in general?
After my graduation in 2013, but the very first year, the first 2 years was very terrible, was very bad, but we improved with experience, huh?
Yeah.
So that's about 10 years.
Oh, wow, that's a lot.
But later I will ask you to do more reading to figure out, understand the knowledge yourself before I will help you to really understand the nature. Okay.
Okay. Yeah.
What's that called? Self-study is very important when you go to university. It is entirely a different level, extremely difficult and challenging compared to high school.
Oh,
But students who study A level with very good performance, like A and A star, they have very good persistence and
yeah.
skills, and so they will get used to the challenge in the university easier than worst performing students.
Mm, yeah. I'm not sure about the last question.
11.
Yeah.
The coil electric motor is made of 200 tons of wire carrying current. The coil is square with side 20s, and it plays a magnetic field of density in Western force exerted on the side of the coil. Okay, it is a rectangle frame placed in a magnetic field, so the two sides of the frame could be in the same direction with the field. And I feel like this.
Mm-hmm.
And use okay, uniform field. So those are the two sides, which is parallel to the field, will not experience the force, zero force here on the top and bottom also. But the other two sides here on the left and right will experience the force determined by left-hand rule, and the value of the force is BIL.
Yeah.
The length is given here 20 centimeter, which is 0.2 meter. The current is 1 ampere, and the field is 0.05 Tesla. 0.05 Tesla. Okay, so this is the maximum force. It is the maximum because the angle is 0. Okay, if the angle is not 0, the force is not maximum, because sine of 0 is 1, which is the maximum value. Okay.
Yeah.
That is question A. Question B, in what position must the coil be for this force to have the greatest turning effect? The plane of the frame, the coil, must be in parallel with the magnetic field lines. The plane of the coil
Shouldn't it be
is
perpendicular?
parallel. Perpendicular, magnetic. Okay. Turning effect. Let me find a different picture. Electric motor. Principle. Yeah. Yeah, like this. There's a field with the frame, the coil. Okay. And the two sides on the left and the right, we experience the two force, upward and downward, creating a torque. Okay. So in this diagram, the plane of this coil is parallel to the field. But what happened to this frame when it is at right angle to the magnetic field? Okay, I cannot find a picture like what I want. So okay, let's draw it. When the frame is at right angle to the field like this, the field is to the right like this. The frame here use the left-hand rule to determine the direction the forces. Okay, this side, let's call them A, B, C, D. The current, for example, run in this direction, down, outward, and upwards. Okay, use the left-hand rule. Field to the right, current into the force here will be downward. On the top side will be downward force. Okay.
Yeah.
At the bottom, the force will be upward because the current is in the opposite direction. The two other sides, AD and BC, left-hand rule again, the field to the right, the current is upward, so the force is into the page. The force is into the page, and here the force is out the page, which will rotate the frame in this direction, clockwise direction. Okay. Force out. Here the force in. I'm sure that it is the plane of the coil is in parallel direction, parallel to the field, which will cause the maximum torque. I still have some difficulty to explain it. It's all deal with the direction of the into right angle like this into. So if it is in this case, there will be zero torque, zero moment, right? Because the plane, the coil is here, like vertical orientation like this.
Yeah.
Force on the outer side of the coil will be into or out of the plane. So it's like squeezing the coil, not rotating it. Okay, squeezing the coil, and also the force on the top and the bottom, we also like squeezing the coil downward. So in that orientation, when the coil is at right angle to the field, there's zero torque minimum. So the maximum torque is when the coil is parallel to the field. Okay.
Okay.
Later we will learn this electric motor. The torque on this principle electric motor will vary with the angle between the sign here, the two sign with the magnetic field. We can make a DC motor like this, very simple DC motor, but from a toy, a model that we can do ourselves with a actual motor with high efficiency, like in Tesla car, is entirely different. Okay, this is the DYI electric motor. We can even do a much simpler thing like this. I'm looking for the simplest thing with simply a battery like this, and DYI electric motor like this, dancing way. Okay, here. Just need to put a magnet at the bottom of the battery. Okay, and then bend the copper wire into a certain form like this, like a rope, a tunnel, and then put this coil so that the top here, the top end, will contact with the battery, and the bottom end will also in contact with the magnet, so that the current can run in from one end of the battery to the other end. Okay.
Oh, yeah.
And it will rotate like this. If you have a piece of copper coil like this and a magnet, you can do it very easily.
Oh, wow.
That is a simple electric motor, or another thing like this. The same principle. Place a magnet in the middle there, and then connect the two ends of this coil with the two ends of the battery poles of the batteries. Okay, and for the electric current running, and also it can slide, can rotate on the frame, the two holder supporter there. Yeah. So yeah, that is the simplest toy, an electric motor. Electric motor in a car. Of course, it is a lot more complicated. The principle is like this. It takes about 10 minutes, so I send the link so that you can see it later. So that is the most important application of the magnetic force that the scientists discovered like about a century ago. Okay, we use electric motor everywhere, in our fan, in our computer, in our refrigerator, in our air conditioning, in hair dryer, washing machine, cleaning machine, etc.
Oh,
Electric motor, like the invention that changed the whole world, huh? What's it called? Revolutionized the world. Okay, let's do question 8 here also at the bottom about the magnetic balance.
okay.
Which current balances with tilt? So it's about using a left-hand rule, determine the direction of the magnetic force acting on the Y, the current. The direction of the field is from the North Pole to the South Pole, to upwards or downwards.
It would be the field would be downwards.
The field goes from north to south. For example, here in this case, this is the current. Okay, the current L, meaning the current goes up like this and go in this direction. For a solenoid coil like this, let me find a picture and put there. Magnetic field created by solenoid, like we studied last time, of solenoid. Right-hand rule. Also. Okay, yeah. Now for the solenoid, you use the right hand, not the left hand. Wrap your fingers around the solenoid, like holding it.
Yeah.
The curve of the fingers in the direction of the current, like that. So the field, like this, okay? So the current points toward my face. So the field generated by this solenoid has the direction like this. This side, there's a problem with the pen. Okay, this side North Pole, this side South Pole. The field go out to the north. Okay. And use the left-hand rule to determine the direction of the magnetic force on the current. In the case A here, field into the page, the current to the right, the force is upward, huh?
Yeah, upwards.
Upwards force. So in this case, it's to upward. This case, the field is out of the page. The current.
Downwards.
Oh, this case is very difficult to like this. Here.
It's downwards, right?
So the finger pointing to my face is the field. This second finger is the current. So the force is the downward.
Yeah, downward.
Downward force. Similarly, for other two cases, the field now from top to bottom downwards. The current is to the right. Oh dear. So difficult now.
Yeah.
Current. Okay. Ooh. See? So difficult. Go with the right hand. There's another way called the right hand rule, which is different from the left hand rule. For the left hand, you have the order F for the thumb, B, I for the first and second fingers, F, B, I. But if you use the right hand, the order is different. I, B, F. I here is thumb, B, F. F, B, I for left hand, I, B, F for right hand. Okay.
Yeah.
So if I use the right hand, I, B is downward. I is it's as hard as the left hand. This case very difficult to use the left hand. A field down, current to the right, so the force is into the page. Force in that direction, into the page. Okay. the question is which case the balance is tilt upwards or downwards. So the answer is A and B. Okay, I guess the last case and the force is outward.
Yeah.
Right hand rule determine where there's no current in. They didn't indicate the current in the coil, so magnetic field and there's no magnetic force.
No magnetic force.
Yeah, because they didn't indicate there's a current in the coil, the solenoid. So the answer is A, upward force, and B, downward force.
Yeah.
Electric motor. Okay, let's see this problem. Electric motor has a rectangular loop of Y with the dimensions shown in the figure here, 0.08 and 0.05. Loop is in the magnetic field, flux density 0.1, which is the B. Okay, flux density. I usually use the word field strength, but actually in A level they use flux density. The current in the loop is 2 amperes. Calculate the torque that acts on the loop. So firstly, we calculate the force FBI, BIL, okay, BIL, and then multiply the force with the distance to the axis of rotation, which is so where's the 2 bar? There's a problem with this one. Okay, we choose this axis to be the axis rotation. So the distance from the force F on the left to this axis rotation is half of this value, 0.08. Okay.
Yeah.
Which means 0.02. And similarly, we calculate the torque of the force on the right and add them together. Or another way is that because this is the force couple, meaning they have the same magnitude and at the same distance to the axis of rotation, which is 0.4. So the torque of the force couple is calculated by one force multiplied with the distance between the two forces.
Yeah.
0.08, which is simply just 2 times of the distance from each force to the exit, or 0.2, 0.4. Okay.
Okay.
So that's how we calculate the torque of this simple motor, not an actual motor. But if when you buy an actual motor, like to make some robot, some toy for a technology class or just a project or something you want to do it yourself, like making a drone, you can buy a motor and you can look for spec of the motor. In Vietnamese, this is you can look into the spec of the motor to see the torque. This is the dimension. This is the power. This is the speed, not the torque. But some other motor they will give the specs, which is the torque. Okay.
Yeah.
Well, not this side. Yeah. Okay. Right. The spec here, we say the power, which is speed. We say the diameter of the rotation axis is the weight. There's no torque. But buying like a motorcycle, very common in Vietnam, yeah, you definitely will care about the torque.
Oh, yeah.
Later. Okay. Share the tab window here. So that is about electric forces between current. Okay, probably we will complete this subtopic by this one, forces between currents. Because each current can generate a magnetic field around it. Okay, a magnetic field similar to electric field can add to each other like vector addition. We call that the superposition of the two fields, or 3, 4, 5 fields. Okay, adding vectors. The current on the left here into the page generate a field which will be determined by the right hand rule, not left hand. Okay, right hand rule. Put the right hand in direction so that the thumb indicate the direction of the current. So the curve of the fingers in the direction of the field. Remember next time, magnetic field of straight current. A straight current will generate the circular field around it. Okay, and remember to draw the circles that are close together when they are close to the current, and further away, the density of the circles are smaller when you draw it further away from the current. Okay.
Yeah. Mm.
And the direction of the field is determined by right hand rule. Yeah. That I explained last time.
Mm-hmm.
So the two currents in this example with diagram will generate the two fields in opposite direction in the space between them. Therefore, they will not actually opposite direction. They will add to each other the same direction. Sorry, not opposite, the same direction. Therefore, the field in the space between the current will be stronger. Therefore, you see the lines, the few lines are closer together compared to on other side. Okay.
Yeah.
And those two magnetic fields interact with each other, just like two magnets. So the two currents can attract or repel each other. They when they run in opposite direction like this, this is north, this is so yeah, north, this is south. The same direction current running like the bottom diagram here, they will attract each other. Why the current running in the opposite direction on the first diagram will repel each other. And I'm trying to explain why they repel each other by magnetic field. North. Like north here and south here, and north here and south here, huh? And therefore they will attract each other.
Oh.
Okay. And this way, north and north here, they repel each other. South and south here, they repel each other. Okay. And we can easily see the experiment to demonstrate that. Forces between two currents. They have a mechanism here, a switch, so that when they put the switch forward, the circuit is in series, which means the current will run like up in the right wire here, okay, and then continue running in the same direction, which is downward on the other part of the wire. Okay, so meaning the two current, upward and downward, are opposite direction. Okay, when the switch is pulled forward. Okay, and when we change the switch to the backward position, the two currents will run in the same direction, and we will see how they repel or attract each other. Now, connecting them to the battery forward, meaning in theory, the two currents are opposite direction. Okay.
Yeah.
Opposite direction, and they repel each other clearly. And then we switch that parallel, they attract each other. And it is opposite to the memory about magnet, like poles repel, dislike pole attract, but like current attract and dislike current repel. Okay.
Okay.
This is a demo. Reading SI unit, explaining the force between two currents. Okay. This is another way to explain why the two currents running in the same direction attract each other. The field generated by the current on the left is a circle like this.
Mhm.
So at the position of the second current, the field of the first current is downwards. Okay, and
Yeah.
we will apply the left-hand rule: field downward, current to into the page. So the force is to the left. Okay,
Oh, yeah.
so that is another way to explain how the current running in the same direction attract each other, and when they run in the opposite directions, they repel each other. Okay, another demo unit comparing forces in magnetic, electric, and gravitational field. You can read these things later by yourself. Summary and read the summary yourself. Okay. End of chapter question. I think we should do this. Yeah. For the last 20 minutes.
Mhm.
End of chapter questions. Have you got a plan? Which major you will apply in university?
Aviation. So
Yeah, like controlling airplanes.
yeah, controlling, plane driving. No?
Uh,
I
One
know.
of my students who was also a Korean student, his name is Hyung-jo.
Hyungjo.
Uh,
Hyungjo? Oh,
yeah, yeah,
yeah. He's my friend.
like 2 years ago. Yeah, 2 years ago,
Yeah.
and he told me that he wanted to be a pilot also, but
Oh,
after he applied for another field. Yeah,
yeah. He just graduated like last year.
yeah, yeah. But I
He
taught him. Yeah, two
he
years
went
ago.
into the nuclear engineering.
Wow.
Yeah. He actually went to the best university in Korea.
Mm. I taught him like only in 3 months, but he was very
Oh,
smart. So yeah, he can
mm.
got like the best result for AP and SAT and A
Oh,
level most. He studied A level most by himself. I
mm.
only helped him from the beginning.
Beginning.
Yeah.
So the first question, it is when the wire is perpendicular to the direction
Yeah,
of.
exactly. Yes. Perpendicular. The angle is 90 degrees. No force when the wire is parallel to the field.
Yeah, parallel. The force will also triple, right? Because they're proportional to each other. So
Yeah, exactly. Yes, because the equation is BIL. Let me write BI first. IBL.
yeah,
Yeah, so it's proportional between force and current. Current triple, force also triple.
Yeah, then it's also proportional to the magnetic flux density, so it should be
Yeah.
half.
Yes. Half the field, half the force. Length reduce 40%, meaning multiplying it with 0.4.
Mhm.
0.4. The force will be 0.4 times smaller.
Mhm. Yeah, times by 0.4. So for this question, do I do 3.8 times 10 to the power of minus 3 is equal to b times 1.2 times 3 times 10 to the power of minus 2 times sine 50 degrees.
Okay. We have the force 3.8 times 10 to negative 3 equal to the current 1.2, the length 0.3, 0.03, okay?
Yeah.
Because that's 3 centimeter, and the field is what we need to find. So dividing this value on the left with the value on the right. And the value of the field is how many? The density, flux density.
0.105.
0.5. We only need two significant figures, which is we can write it to 1.
Yeah.
Tesla. Okay, we should be written as 3 times 10 to negative 3, negative 2, so that we can simplify calculation. Huh?
Yeah.
It's better scientific notation. What is the direction of force given by the y? Okay, still just left-hand rule.
Yeah.
The current run in this direction, making angle 50 degree. You can use the vector resolution to consider the current as two individual current, which one current at right angle to the field, like this. You see a part of the current, I1, a component of the current, okay, and the other component parallel to the field line. And therefore, this parallel component experiences no force, I2, okay?
Yeah.
So I1 is like I times cosine psi, I1 like resulting in that direction. This is 50, this is 50 degrees, so sine of 50, okay? So
Yeah.
that is the reason why in the equation of F equal IBL, we have sine theta. Let me move I to the other position, which is here. So that the whole thing here is the component of the current, which is perpendicular to the field, okay? And the component I2 parallel to the field experiencing no forces, okay?
Yeah.
No magnetic force. That is the reason why it is a sine in this equation, sine theta. Sine 50 degree, okay. The direction using the left-hand rule also, the field is downward like this. You can even, downward like this. The current is I1. Current I1. So the force is into the page. Okay. The force into the page.
Into the
Left-hand rule.
page.
Into the page. Left-hand rule. The left-hand rule usually denoted by this letter, left-hand rule. Now moving on to question 4 and 5 and others. 4 here.
For this question, do I take a photo and send it to you? Because I have to draw.
Uncover the dramatic view around between two strips. Yeah, you should draw on your notebook. On the copy, which means you need to draw a new one yourself, not on the given diagram, given objects. Okay.
Yeah. The direction of force is towards each other, right?
Between the two strips. Yeah, because they are running in the same direction. The strip carrying downward into the page. Yeah. Yes, they will attract each other.
Yeah.
Running in the same direction. The same force, Newton's third law, okay? Not different forces, different magnitude. Newton's third law, action and reaction forces. Explain. Okay, you can explain by a way like this. The magnetic field generated by a current on the left at the position. Let me type it here. Change the color. Okay, the magnetic field generated by the current on the left at the position of the current on the right is which direction? I'm using right hand rule into downward, huh? It's downwards. So according to left hand rule, the left hand rule, the magnetic force acting on this current on the right, we can call it the second current, okay, is field downward current into is to the left. meaning toward the first current. Yeah. And similarly, the magnetic force on the current on the left is to the right, which obeys Newton's first law. So this is this additional information, okay, on Newton's first law. Okay, let's say for Marx, we need to explain that very clearly.
Mm-hmm. Yeah, okay.
Okay, I think that is enough for today. I need to take a little rest and teach another student, which is also a student foreign at the same school with yours, but 1 year earlier.
Mm-hmm.
So let me export this board and send the file to you on Viskai also. I will make a Google Drive and save all the notes and documents during our learning process in there. Okay?
Yeah, okay.
So see you this Sunday, right?
Yeah.
Do you need to study, like really need to study this Sunday? Because let me check the calendar. October, wait. It's okay for me. Never mind.
Yeah.
I was thinking of taking a day off, but okay, I think you can do that. Because I have 2 other classes off that day for a, what's it called? Anniversary in Vietnamese Teacher Day.
Oh, yeah.
But okay, see you on this Sunday, 3 p.m.
Yeah, okay. Yeah, see you.